Good. Yeah, so as I said, we want to solve different tasks with different networks which we looked at previously. Most of the work here has been done at Berkeley AI Research, and now I just switched to first letter to Facebook AI Research. So more general, what I want to do is like understand communication about the visual world as humans can do it. And humans can ask questions and answer them, for example. But we want to bring that also to like an automated system, for example, your phone, which could answer you, can I park here? And answers no. And this can be actually quite, such a question can be very complicated. So you might need actually something like a program to answer this question. And first detect if there's a red curb, see if there's space to park there, and then actually you may be able to answer if you can or cannot park here. So that's what we want to do. We want to basically predict a discrete execution graph of neural networks to answer diverse diverse natural language questions. But then this is not very helpful to understand for most humans because typically you don't want to understand the code. So most humans don't want to understand code. So we want to also explain our decisions with natural language and say, for example, because there's a red curb, which indicates no parking, instead of just showing a program. So we want to explain answers for understandability and trust. And I'm mainly going to talk about these two works. I'll start with learning to reason, end-to-end module networks for visual question answering, which will appear at ICCV. So the problem is, for example, such as this one on the Clever data sets, which have very complicated questions. So that's why it's an interesting test bed for our algorithms. For example, here, how many other things are on the same size as how many other things are of the same size as the green mud ball? And how do we want to do it? We want to predict a neural network which consists of different components, and then execute this neural network to answer this question. And all of these components are basically small neural networks which we put together, then execute jointly. So let's look into more detail what this question means. So first, we have, for example, a find module which gets as input the green mud or the green mud ball. So it predicts automatically where to attend to in the text. And then it localizes exactly this region. And given this attention, here now you see the attention, sorry. Given this attention, we then do the next step and look for things which are of the same size. And again, we basically attend to all the regions which are of the same size, and then we can finally count them to answer how many other things are there. And here in this case, we get it correctly. It's 4 other objects. So let me give a few more details, but I would like to say that we cannot just only do that for like linear execution graphs, but it can be also trees, like you can see here, and it can also be executed on real images. While for the most of the talk, I'll stick with these Clever dataset examples. So here's basically the sort of the overview of the entire network. And basically we take in the question, we encode it with an RNN, and then we predict the execution graph at each time state of a decode RNN. And each of the modules, which you can see here on the right, attends to parts of the text. And then we build this network, which gets attended text features input and either attentions or different image features. We execute it, and then we predict the answer. to be able to learn that, because there's discrete steps we have to do, we use reinforcement learning to optimize it, where only the answer is used to reward the reinforcement learning. And yeah, so there's like sort of a large variety of modules which we have, and they can be defined in whatever way you need them for your problem. But for the clever data set, and specifically, we came up with those kind of modules. And you see they have either attention, so A as input, and or image features, and they typically output either an attention mask or then a softmax answer, because in the clever data set, you just need a softmax. You could also add an RNN as output if you want to really predict text as output. Maybe one more detail I'm missing is that, yeah, we just train it with question, answer, and image pairs. And we start with an expert. We start with an expert policy, and then fine-tune with the reinforcement learning our policy. And in the clever data set, the expert policy is just given by the data set, because all the questions are constructed automatically, at least in the first version of the data set which we use. Let me show you some examples. So first we started on the shapes data set. Here we can see, do you have a question? Ah, okay. So we started on the shapes data set. We compare with the neural module networks. We have ours with cloning from the expert, get solve basically the data set, and which when we just don't use any expert policies, so just learn the policy search from scratch, we get close to perfect performance. And here you see two examples about the two different setups, behavior cloning from the expert policy and policy learning from scratch. And we see typically the policy learning from scratch finds sort of simpler execution graphs. And both, in this case, both answered correctly. We also evaluated on the larger clever data set, and at the time of when we submitted that, we significantly outperformed all prior work in that. And again, we compare, here we compare only cloning the expert directly and using additional policy search to refine the module layout. Maybe it's more interesting to look at a qualitative example. It's maybe a bit small to see it, but here we correctly predict this tree, because at test time we don't have any ground truths for the questions, at least we assume we don't have it. So for example here, this find module directly predicts that it has to look at right, and the other find module looks at blue cylinder. So the attention is mainly at blue cylinder, and then sort of it relocates it and filters it, and then it compares these two outputs to answer the questions. Does the blue cylinder have the same material as the big block on the right side of the red metallic thing? The last result I'd like to show is like that it also works on the VQA dataset with real images, but that's much more challenging to make this network outperform prior work. So we just get like state-of-the-art performance. And so this is sort of the first part of my talk, and I'm happy to take already question at that point, because the next part will be about slightly different work. So if anyone has questions. Okay, then I'll continue. So what I said now is basically we can answer questions. Now in the second part of the talk, I discuss how we want to explain them with natural language and also with grounding. And I'll say a bit more to that in a second. So this is the work attentive explanations, justifying decisions, and pointing to the evidence. So we have the scenario, what is the person doing? The answer, skiing. But then if you might want to ask, why is this actually the case? Or how do you know that this person is skiing and not hiking, for example, through the snow? And what we want to do, we want to predict, on the one hand, a textual explanation, for example, because the person has skis and poles and there's snow, and also a localization of this. So like similar to humans, which can explain you things and point you to why this is the right answer. So in this case, the skis and the poles might be the most discriminating factor for the answer skiing. We want to do the same thing, allowing machines to do that. As I said, not in this work, we don't actually use those modules, but we're using a more end-to-end approach, and it's on the real VQA data set. So prior work from ourselves did already generate explanations on the CAP birds data set, but there's actually no explanation ground truth. And we found, while in this work we could actually start off with the descriptions and learn explanation models, this is much more difficult on the VQA data because it's much more diverse. So what we did, we started with the Microsoft COCO VQA data set, and additionally collected both textual explanations for 20,000 images. We collect about 30,000 textual explanations, and for the small test set, we also collected ground truth pointing or attention maps based on what humans think is the most relevant part of the image to explain the answer. We not only did that for VQA, but also for, so this is the MPI human post data set. I think Svetlana also talked about this data set. And here we also collect additional explanations and ground truth attention maps. And we show a bit how this data looks like. For example, while descriptions say, for example, a man on a snowboard is on a ramp, the explanation, textual explanation for what is the person doing snowboard is they are on a snowboard in a snowboarding outfit. Or instead of a gang of biker police riding their bikes, information down the street, the answer to the question, can these people arrest someone? Yes, and the explanation is because they are Vancouver police. And we also have corresponding ground truths for the pointing task. So like pointing where it's like skiing, where skateboarding, where's baseball, where is it like grounded in the image. And as I said before, we did similar things for activities. Here you see some textual explanations, and here you see some grounding explanations. Yes?
Is the grounding explanations asking somebody to segment the objects that are related to the question?
And the answer. So the Turkers get the question and the answer which you see, they don't get the explanation. And then they have to sort of say, where do they think is this explained in the image? And doesn't need to be like this, what sort of they think?
Surprisingly detailed, or like surprisingly precise, like the skiing.
So it's not always as precise. So like we collected 3 per question answer pair. Sometimes they're less precise. This, I'm not. I think I didn't put like different variants in. My slide crashed and I forgot that slide to put it in again. So we start off with our last year's model from the VQA challenge, but we slightly modify it and replace the MCB pooling with element-wise multiplication, and importantly, use the convolution over the input of the question because it's not of the image, and sine squared NL2 normalization. And with this, we get actually performance that is slightly better for a single model than MCB or last year's model. And there's actually a contemporary work from Kim et al., and they use a tanh instead of sine square and L2 norm, and they also get slight improvements over the MCB model while keeping everything else fixed. So interestingly, already the VQA model gives you like a good idea where to point to because it has this attention mechanism. So we have this first answer attention, and then I now slightly switched the visualization, but basically this is the VQA part. And then we add a second attention mechanism to predict the answer. So basically, we take the input, the predicted answer as input, and the visual features, predict again an attention, and then predict the output description. And now we can see sort of how good are both the textual explanations and the groundings of these attention masks. And first, we evaluated the textual justifications, and both with automatic measures, we see that our model improves over several base lengths, including the one of Hendricks et al. For our previous explanation model, training our model on descriptions only, using a captioning model, or ours without explicit explanation attention. So just not using the second attention, just using the first one. And similar is true if we do a human evaluation, also our model performs the best. And this was on the activities. For the VQA, the performance difference of the benefit of the second attention is not so big, but if we fine-tune the VQA model, it gets slightly better. We also evaluated the pointing, and we used on the one hand the Earth-Musev distance, which takes spatial proximity into account. So if things are close by and the model predicts things close to the correct pointing, then it gets still some of the score. And we see that our fine-tuned model for VQA gets best performance, and we also evaluate on the VQA head data set from Das et al., and we also see that our fine-tuned model significantly outperforms the previous ways to look at attention. And I think the second point, which I think is interesting, is that the explanation attention, so the second attention, which we introduce by actually explaining the model with natural language, gets consistently better performance than the answer attention. So you can see that both on this evaluation with rank correlation and also in this evaluation, it's typically slightly or quite a bit better to use the second attention map. Some qualitative results. I think it's always interesting to look at sort of where only part of the thing changes. For example, here we have the same image and different questions. So is it sunny? Yes. And what is the person doing surfing? You see we get different predictions of the both in with respect to textual explanation and the pointing explanation. Or the other way around, if you have the same question and answer but a different image, we get also different justifications and different pointings. There's some more examples, but maybe at this point let me conclude the talk. So we learn to predict neural module networks with an end-to-end model learned from images, question, and question-answer triples. And we use imitation learning and then reinforcement learning. And we have results on both clever and real VQA. And for justifying decisions and pointing to the evidence, we collected a data set. And our model can explain decisions by pointing and by giving a textual justification. And interestingly, when you learn the pointing with textual explanations, that improves in better pointing performance than the normal attention model. With this, it's not your time to ask questions, and you might ask, what's next? I'll tell you that we have like a movie VQA challenge, and that will be at ICC3. And yeah, thank you to all my collaborators, like specifically Rong, Hang, and Sess, who did like the majority of the work, and this was a joint work with Kate, who will give like the next talk.
Maybe we can have only one question.
Yeah, thanks for a great talk. I do have one question. So when you try to illustrate the reasoning, or I mean the explanation or point, it's more like an empirical attention heat map, or do you have some more like model level explanation why this is picked? Or I'm thinking of like recently, for example, people talk about neurosymbolic reasoning or this.
You mean like in the first model? Yeah. You mean like in this explanation part, or in
the explanation part?
Okay. You mean like how, if this is correct? I'm not sure what the question is.
Yeah. So if even your model can infer the attention map like this, it's more like you compute the attention and then highlight it.
Yes.
So is there a deeper understanding for why this? I mean, at the symbolic level, why this is the explanation of this answer?
We don't know why it's the explanation. The only thing we can do at that point is to evaluate it if it matches what humans think. That's a good pointing explanation.
I see. So this one is what humans think. When humans.
So this is what humans think, and basically in this evaluation here, basically we compare how close is what humans think to what our machine thinks.
I see. Okay, great. Thanks.
Let's have the speaker again. So our next speaker is Kate Saenko, and Kate is assistant professor at Boston University and leading the computer vision and learning group. She has done a lot of interesting work in computer vision language and also in domain adaptation, and including the describing videos, some of the early models from the attention-based VQA and image captioning and recent modular-based VQA. So Kate is going to give a talk about why do you say that, explaining and diversifying image captioning models. So we are looking to hear from you, Kate.
Okay, thank you for the introduction. Can everyone hear me? Yeah. Okay, hi everybody. Thank you to the organizers for organizing the workshop and for inviting me. And I'm going to continue on some of the themes that were brought up already this morning. In particular, I'm also going to talk about explaining vision and language models, which is something that Marcus just talked about. But I'm going to tell you about a different model for doing that. And I'm also going to talk about how can we diversify these models so that they don't only learn about objects that are present in their training data sets. And so that is something that Lana alluded to this morning as well. How can we transfer knowledge from auxiliary data sets? First I'm going to start with explaining. And so this is work that was actually presented at this conference, and it's joint work with my students, Vasily and Abir, my postdoc Abir, and Jianming Zhang at Adobe Research. So I'm going to talk about captioning models, but I hope that there are many lessons here that are applicable to open-ended visual question answering. So in captioning, our goal is to take an input image or video in this case. I'm going to talk about mostly video captioning, but also some image. And then use use that video as input to a neural network that then predicts a caption. It's a variable length sequence of words that describes the main activity or the main content of the image. But what I'm interested in particular is why is the network predicting the caption? Right, so the question that I'm going to talk about today is why did the network say that? And one of the reasons that I became interested in this is that if we take this captioning model, for example, and you might want to guess maybe the network said, this a woman is cutting a piece of meat because it detected the person, it detected a woman. But then we run this experiment where we train two versions of the network. One we train on cooking videos, and another we train on science videos. These are tags from YouTube. Okay. And so then now if we feed this exact same video into the first network that was trained on cooking, it predicts a sentence that starts with "a woman is," and when we feed it into the science trained network, it starts the sentence with "a man is talking about." So clearly the network is learning some biases in this data, but also shows us that the reason that a network might predict certain words really has more to do with the language model than what it actually detected visually in the input. So in this work, we wanted to understand what did the network actually see and what did it say based on what it saw in the input video or image versus something else that it inferred from language and not from vision. Okay? So we want to know, in particular, we want to explain the predicted caption words by seeing if the network can actually localize objects that correspond to words in those captions. Okay, so so in this work, apologize, video is not playing for some reason. Okay, I'll go to my backup. So in this work, we presented an explainable neural network for captioning images and video. Oh, thank you. Something went wrong here. Just give me a second. Sorry? No. Okay. Yeah, it doesn't want to. It doesn't show the video. Okay, I'll just do it without the video then. Sorry about that. So basically, in the video that is not playing, you would see a model that can explain the caption words using what we call top-down visual saliency. So basically, what we want to know is some sort of attention map or saliency map on the input that is related to each of the words or phrases predicted by our captioning network. And this is very related to what's known as attention or attention layers or soft attention models, which add special layers to a network that sequentially process regions in the input image and basically learns which regions to look at using this attention layer. So this is, was proposed by Xu et al. At ICML 15 as a model called Show, Attend, and Tell, and has been used fairly extensively to sort of add an attention layer to various networks. So some of the issues that we had with this as an explanation model for visual captioning is that it, first of all, this only provides us with spatial attention maps, and what we really want is spatiotemporal. And if we add layers for spatiotemporal, you know, we were adding a lot of parameters to the network. And the other, so our motivation is how can we actually analyze the network as is without modifying it, without adding extra layers or parameters, just get out what is its implicit attention. So the key idea was to essentially probe the network with small parts of the input. So our network in this case is an encoder-decoder network, which is fairly standard at this point for captioning and video captioning. And so what we want to do is we want to take the sequence of input. Here I'm showing frames of the video. And we want to just take one frame and probe the network with that frame and see what is the probability of the output word in the sentence. So this will lead us to a way to compute spatial and spatiotemporal saliency map. And the nice thing is that we don't need any special attention layers, and we will get spatiotemporal attention for free, essentially. Okay, so just very quickly how this works. So the base model we're using is this encoder-decoder network, which takes video frames, applies a CNN to compute convolutional features, which you see here, 8 by 8 by 248 grid of convolutional features. And so this is for one frame I'm showing you this for one frame of the video. And then these features are average pooled to produce a single 248 dimensional vector. Now this vector represents all the semantic content of that frame. So these frames are encoded by an LSTM encoder, and then that state is fed into an LSTM decoder, which predicts the words. So what we want to do now is we want to take, as I said before, a small piece of this input. And so we start with essentially taking one convolutional neuron output, so just one vector corresponding to one location in that grid, and feed that into our encoder-decoder network, and then look at the log probability of the corresponding output words in the sentence. And so we continue this for all of the locations in one frame. We get this grid of values. Now, this is still not what we want because it's not normalized. So for example, for some words that are not informative, like a or is, the attention is essentially high at this point for all of the locations. So what we do next is we do this for all the frames in the input video, which is what you see at the top right. And then we normalize it, obtaining the heat maps that you see on the bottom right, and then interpolate so that we can show smoother heat maps. So that's the final result. And so if we go back to this video that I showed you in the beginning, where the model predicted a woman is cutting a piece of meat, now we can see, we can actually visualize using this approach, what is the frame that had the highest saliency for each of the words in the caption. And so these are the frames that I'm showing you here. And then also in each of those frames, we can see the spatial attention that was predicted by our model, which shows the visual evidence. And here we actually see that, for example, which of the visual features led to the word cutting and the word piece and the word meat. And also for the woman, we see that it's actually not a very consistent attention map for the woman, which kind of correlates with what I said earlier, that the model just may know that if it sees a cooking scene, a likely way to start the sentence to say a woman is cooking. Here's another example. This is a video that was captioned with a man is talking about a phone. And I'm showing the most salient frames at the bottom for man talking on the phone. And again, here we see a fairly consistent map for the man and the phone. Not so much for talking, which kind of makes sense because a lot of these videos, you don't actually see, visual evidence of people talking. You might hear them talking, right? But the network here is inferring that talking is an appropriate word to insert. If it wants to say a man, on the phone, something is happening, a man is describing a phone, we're talking about a phone. So that could be coming from the language model. Here's another example. A woman is skating on the snow. So we can actually use this to understand why a model made mistakes. Right, so here it said skating instead of skiing, which was the correct caption in this case. And if we look at the saliency map for the word skating, we see that actually is mostly located on the white parts of the frame, the snow essentially. So it's seeing snow, or maybe it's just thinks it's ice and it's just something white, and it's correlating that with the word skating. Yeah, and it's similar for snow. Okay, so we evaluated this model. Unfortunately, we didn't have a data set that had spatiotemporal ground truth for salient regions in videos, so we instead applied it to image data set. And so we can do the same thing for images. We can caption images with this model if we slide a window across the image, and that gives us our sequence of frames, essentially. So we applied this model to image captioning, and here's one result. So the input now is a single image, and the caption is a man in a jacket is standing at the slot machine. Here you see the saliency for man, for jacket, standing, slot, and machine. And for the most part, it makes sense. The model is sort of pointing to relevant parts of the image, except for standing, perhaps. That doesn't seem to be getting any visual evidence for that. So to evaluate this in a quantitative way, we used the Flickr 30K entities data set, which Lana talked about this morning. So this is a large data set that's annotated very extensively with both captions that you see on the bottom. So there are multiple different captions for each image. And the nice thing about it is that for each phrase, like noun phrases like pierced ears or glasses or an orange hat, each of those phrases has a corresponding bounding box annotated in the image. So we use this data set to play a pointing game and evaluate our model in terms of both pointing accuracy. So here pointing is defined as, if we take the most salient point in the image, did that land inside the bounding box for that phrase or that word, right? So for example, here, an elderly man is, the saliency for an elderly man is in the far left image. And, that is actually pointing inside the bounding box annotated for that phrase, an elderly man. So, and we also evaluate, based on the heat map, the attention overlap. So we look at how much this saliency map overlaps with the bounding box. So, so to evaluate the correctness of our attention map, we compare it to several baseline methods like just random attention map, or essentially attention on everything. And we also compared it to soft attention. So soft attention in this case gets about 38.38 score of this attention correctness metric. And we see that with our model, we can improve that to 47%. So, so our model is actually doing better than this approach of adding an explicit attention layer to the model, and then having that layer learn sort of to associate which of the locations go with which words. So we also evaluated captioning performance, see that this model does as well as others on captioning, so it's not affecting the quality of captions. So 5 minutes. Okay, so since I'm running out of time, I'm just going to skip to this next part of my talk and talk about very briefly. So I talked about explaining, and I also want to mention diversifying, which I think is very important for language and vision models. So the problem with language and visual models is this issue of lack of training data. Right, so in object recognition, for example, we have 14 million images in ImageNet, 22,000 classes, so we have this plenty of annotated data for object recognition. But if you compare that to something like visual description or captioning, the annotations of images with captions only contain about 80 classes of objects, right? So it's a pretty limited set of objects, just because it's difficult to collect these data sets. So what we want to do in this work is propose a captioning model that can take learn both from paired image and caption data. So for example, MS COCO captioning data set. And so in this kind of data, we'll have words like a horse, for example, but this input image is not a horse, right? This is actually some other object, which doesn't exist in our captioning data set. So what we want to do is we want to take the ImageNet data set, which has images labeled with this object category. This is a no copy. And we want to combine it somehow so that the model can learn to transfer this knowledge and insert it into a sentence, right? So we don't want just an image captioning model that will just say "okapi," right? We want it to output a sentence describing the whole scene and insert that novel word "okapi" in context in the sentence. So we wanted to say something like an okapi standing in the middle of a field. So, so we proposed this model, and this was presented earlier in the conference. The main insights here are to recognize and describe objects using outside data, so not just image caption data sets. So we want to train effectively on external sources of data. And second insight we used is that we want to somehow transfer similar objects between our data sets. For example, we want to somehow inject knowledge in the network that okapi is similar to something like zebra. And we did that by using semantic embeddings, semantic word embeddings. In this case, we used glove embedding. So with glove embedding, we automatically get this mapping from, for example, zebra, which occurs in MS COCO, and okapi, which is close in that semantic embedding to zebra. And so then we combine these two parts into a captioning model. But you might say, well, this isn't really different from existing models. But the problem with this is that it leads to catastrophic forgetting. So if we fine-tune or train this model on captioning data, we'll forget all the objects it learned about in ImageNet. So the final insight here is to overcome this forgetting by training jointly. So we propose a joint loss that we use to train simultaneously on all of these data sets. Okay, so that's the main high-level idea. I'll just show you quickly some examples here. There's an evaluation in the paper if you're interested. But here are some examples qualitatively. So these are objects that are ImageNet objects. They don't appear in MS COCO captioning data, but our model can still caption them in context. So for example, it can say, a small brown and white jackal is standing in a field. So it's transferred the word jackal from ImageNet and inserted it into this caption, so it's properly captioning that specific object. There's some more examples. So this one on the right, a woman is posing for a picture with a chiffon dress. So chiffon is, again, not something that exists in the paired COCO captioning data set, but the model learned it from ImageNet and inserted it into the sentence. Okay, so I'll end here since I think I'm pretty much out of time. I want to thank again my co-authors, my students at Boston University, and also Subhashini, who was the lead author on the novel object captioning work, and also Lisa Ann Hendricks, Marcus Rohrbach, Raymond Mooney, and Trevor Darrell. And thank you.
We have time for one question. Questions?
Thanks. I think it's quick. I noticed sometimes it says something like a corkscrew and a corkscrew, or a copy and a copy. Is that because it's substituting for two different words that were there originally with the same word? I mean, was it, or the cougar with the cougar in its mouth, was it?
Very, very perceptive. Yeah, so actually I had this slide that I didn't do, but yeah, so one of the common errors of this model is repetition. So we'll say balaclava, black and white photo of a man in a balaclava. And we're not quite sure, or yeah, cooler with a cooler in its mouth. So we're not quite sure why it's doing that. One guess is that, you know, the model has some strong evidence for that particular word, and it's just, you know, it's a high probability word. And it's maybe that the language model hasn't fully learned, you know, how to not insert it more than once. So, good question.
Thank you, Kate. We'll now be taking a 15-minute break, and we'll be resuming at 10:45. Thank you.